Welcome to The Explainer. Let's get right into it today because we are literally prying open the ultimate black box. We're going to look under the hood at the internal reasoning mechanisms of frontier AI models. We're talking about visualizing exactly how these massive systems actually think through complex problems, step by step. And we're going to do all of this by unpacking some incredibly fascinating, brand new research from Google DeepMind. Let's dive in.
Now this right here is the million-dollar question, isn't it? For years, the massive debate in computer science has been this. Are large language models genuinely reasoning their way through complex problems? Or are they really just reciting memorized semantic tricks? I mean, are they just a highly advanced, spicy autocomplete guessing the next most logical word based on mountains of training data? Or can they actually simulate a world in their mind, look ahead, and generate a rock-solid multi-step plan?
Okay, to figure this out, researchers brought in the prime suspect of our investigation, the classic blocks world test. The setup is simple. You have a messy table covered in stacked, numbered blocks, and the AI has to figure out the exact sequence of moves to stack them into one specific perfect goal tower. Now, for a human looking at a picture, it's child's play, right? But here's the catch. The AI doesn't get a picture. It just gets this scrambled, totally text-based list of rules. Things like block 7 is on block 4, and block 8 is on the table. From just that text, it has to build a physical plan completely blind.
So here is our roadmap for the explainer. 1. Can AI actually plan? 2. The path star graph analogy. 3. Removing semantic cheat codes. 4. Serial algorithmic simulation. 5. Crushing classical AI planners. And 6. The future of agentic AI.
Moving right into Section 2, the path star graph analogy.
This is where things get mathematically beautiful. It brilliantly illustrates a concept called isomorphism, which is basically just a fancy word for a direct structural match. That messy physical table of blocks we just talked about, well, mathematically, it is identical to a graph topology. Think of the physical table as the central root node, and every stack of blocks sitting on it is just a disjoint branch radiating outwards.
So the key concept anchoring all of this is the path star, or P-star topology. For an AI model reading text, finding a specific goal block buried deep in a stack is exactly the same as finding the correct branch to traverse in this path star graph. It has to trace a path back from a distant leaf all the way down to the root. It's essentially a dynamic graph traversal tracing invisible dependency chains.
To actually solve it, the model has to get into a really strict three-step rhythm. First up is branch identification. It searches its text context to pinpoint the exact branch holding the goal block. Second is iterative clearing. It has to work top-down, moving everything off that specific tower onto the table until the target is exposed. And third, goal placement. It picks up the newly exposed target block and stacks it. It has to execute this loop flawlessly, over and over, from the bottom of the goal tower all the way to the top.
Which brings us to Section 3, removing semantic cheat codes.
But wait, here comes a pretty massive twist in the research. What if the AI is just cheating? Like, what if it's only doing well because it already understands real-world semantics? It knows what a table is, it knows what stacking means, and it intuitively gets gravity from reading billions of web pages. So to prove what was really happening, the researchers ran a genius test called the graph rewrite. They totally obfuscated the problem by stripping away all physical semantics. No more blocks, no more tables. The whole thing was translated into abstract, completely meaningless graph rewriting commands. Node IDs, operations like detach node and attach to root. Suddenly, the AI couldn't rely on common sense real-world logic. It was flying completely blind in abstract math space.
As the researchers put it, this radical reformulation ensures we are isolating genuine structural reasoning rather than just testing if the model remembers a learned task. If the AI can still solve the puzzle when it's disguised as bizarre, abstract node detachments, then it totally proves the model isn't just regurgitating its training memory. It proves it is actually capable of on-the-fly, complex structural reasoning. And spoiler alert, reasoning-enhanced models absolutely crush the spline test. No problem at all.
All right, Section 4, serial algorithmic simulation.
So how exactly is it pulling this off? Well, when you map out the AI's thinking trace length against the optimal plan length, you see something incredible. Basically, we're measuring how much internal computing effort, how much thinking the AI uses before it spits out an answer. The data shows a strict, perfectly linear trend. The model is using a dynamic budget of reasoning tokens to systematically search the problem space, and it scales perfectly step in step with the complexity of the puzzle.
And that data reveals a magic number, 47. Researchers discovered a strikingly consistent ratio of roughly 47 thought tokens generated for every optimal plan step. Why is that mind-blowing? Because it proves the model is executing a serial algorithmic simulation. It isn't just taking one giant lucky parallel guess of the whole problem. It's using those tokens as a literal working memory buffer, running a step-by-step depth-first traversal of the PathStar graph inside its own mind. It spends a reliable 47 tokens of sheer effort for every single logical step it takes.
On to Section 5, Crushing Classical AI Planners.
So what happens when we scale this up into a massive, grand challenge? Imagine increasing the height of the towers, the number of towers, and the number of goals all at the exact same time. Well, older classical AI planners completely collapse. They hit a computational brick wall almost immediately because the search space just explodes exponentially. But reasoning-enhanced LLMs, they handle that massive combinatorial complexity without breaking a sweat, tracking perfectly along the theoretical optimal path.
To sum up that contrast, classical planners hit computational hard walls and basically give up on being optimal just to find any solution at all. Reasoning-enhanced LLMs bypass that completely. By logically breaking down the PathStar graph step by step, they maintain perfect theoretical optimality. But, and this is a big but, they aren't invincible. Once the problem finally exceeds its internal thought token budget, the LLM hits a sudden zone of instability where it just totally fails. It doesn't slowly degrade, it basically snaps.
Finally, Section 6, the future of agentic AI.
So why does all of this matter for us? Well, knowing that LLMs can serially decompose complex PathStar graphs into completely logical, independent subproblems totally changes the game for building agentic AI. Think about it. If you can break a massive, intimidating problem down into tiny, simple serial steps, you don't actually need massive models with huge generalized semantic hubs for every single action. Suddenly, hyper-efficient small language models, or SLMs, can shine by just executing those simple subtasks perfectly. On top of that, mapping out those binary instability zones is absolutely crucial. If we know exactly when and why a model suddenly snaps under complexity, we can actually build safe boundaries for real-world AI forecasting and high-stakes decision-making.
Which leaves us with one massive, provocative question to chew on. As AI continues to master this kind of internal algorithmic simulation, literally running code and tracing complex graph topologies entirely within its own latent space, what complex, real-world systems is it going to autonomously unravel next? Are we talking about global logistics networks, genomic sequencing, supply chains? Honestly, we are just scratching the very surface of what reasoning-enhanced models can really do. Thank you so much for joining me on this explainer, and keep learning.